Welcome back. This is the last example, example 4 for the inverse Laplace transform. This is page 30 of our slides. Let's take a look at the given XS. Looks very complicated. We have 6s, 6 times bracket s plus 34 at the numerator, and we have s times a quadratic functions below. Let us first break this quadratic function to find the roots. So if you combine these two terms, you will get these quadratic terms here. So what we have is a complex pole. We have 5 minus j3. So let's now draw where they are in the S domain. So if this is the real plane of S, and this is the imaginary plane of S, and of course this is 0, and this is 1, and this is 2, and this is minus 1, and minus 2, and so on. Right. Let's ignore this first, and let's call this at minus 5. This is plus 5. Then they say this is 2.5, this is minus 2.5, and let's say this is 3j, and this is minus 3j. Okay, so we have this as the real line, this as the imaginary line. Let us find where is this guy. So it will be s plus 5 minus j3 is equals to 0. Therefore, s is equals to minus 5 plus j3. So, because this is sitting at the denominator, this is a pole. A pole is denoted by a cross. So at minus 5 plus j3, I'm going to draw a green cross for you here. So this is the green cross. Now I'll draw for you the purple cross. Who is the purple guy? It will be s plus 5 plus j3 is equals to 0. Therefore, s is equals to minus 5 minus j3, which is, of course, here. So I have a positive pole, a pole at minus 5 plus 3j, and a pole at minus 5 minus 3j for these two expressions. What about this guy? Well, it is a pole at s equals to 0. So I'm going to use a different color, which is blue. So this guy will be here. So there are 3 poles for these 3 functions. Now, don't worry if you don't know how to put the poles positions with respect to this. We'll come to it here. But what I want you to focus on is this guy, this pole, which is have this associated expression here. Okay. Again, you have to solve for k1 and k2. It is not difficult but highly error prone. So the answer for k1 is 6. For k2 is a complex number. Right, so now we have k2. Let's focus on the k2 first. We have minus 3 plus j4. Where is minus 3 plus j4? Let's again draw another complex plane. And where is minus 3? So minus 1, minus 2, minus 3. So it's minus 1, minus 2, minus 3. Where is plus j4? 1, 2, 3, 4. So it is somewhere here. And I draw a point here. And this point is minus 3 plus j4. I want to find the magnitude, which is this guy, and the angle, theta. Okay? Now, the magnitude is easily found. It is simply, you can form a right angle triangle here. And this is this length square, which is 3 square. And this length square, which is 4 square. So this length is equals to 3 square plus 4 square square root by Pythagoras theorem. Okay, so the answer is 5. Let's try to find theta. So theta is here. Theta is the angle of the vector anti-clockwise from the real line. So this is the real line. Anti-clockwise is from this real line to the vector. So this is theta. But well, how can we solve this? Let's solve for another angle first. Let's call this angle gamma. Tangent gamma equals to opposite, which is 4, adjacent, which is 3. Therefore, gamma equals to arctangent of 4 over 3. And then in radian, it is this value here, 0.927 radian. Alright, but we're interested not in gamma, we're interested in theta. Therefore, theta is equals to pi, because we are interested, pi is here. So it's pi minus gamma, which is 3.1416 minus 0.927, and the answer is 2.214 degrees. 214 radian. Now, later on you'll see a degree somewhere, which is very strange, but never mind. We convert our radian to a degree. 2.214 radian is equals to 126.9 degrees. Exactly this one. Okay, so we have found theta, and we have found the length, which is 5. This will become useful because this is K2. K2 is here, and it will be useful for us later on. Where do we put K2? Here. It will be 5 with the angle theta. And what about the last one? You realize that the last one, K2 conjugate, it is because this thing comes in pairs, and we have conjugate, which is also magnitude 5, but the angle is now minus 1 to 6.9 degrees. Now, I will not go through the math, but this pairs of rational function will be converted into here. So let me show you how to convert from these guys, this thing here, to this thing here. Alright, let's pull out the important numbers. The important number is 5. So, where's the 5? You realize that this thing, pole comes in complex conjugate pairs, you will form a cosine. The amplitude is 2 times 5, where this is that 5 we're talking about here. So it becomes 10. We have a cosine here, and where's the 3? The 3 comes from here. This is the 3. What about 126.9? Comes from here. And then the last number 5 is put into here as minus 5. So notice that this very complicated expression which actually have 4 important numbers, the magnitude and the phase is put into here. 2 times the magnitude and the phase. What about the other 2 interesting numbers? 5 and J3. 5 is put here as E minus 5t, and J3 is put here, 3t, the frequency of the cosine. So please learn this, and in another tutorial or in other lectures I will derive why this is so. But here just recognize that this is how we put our terms into the expression here. I forgot about K1 over S. K1 over S is 6 over S. The inverse Laplace transform of 6 over S is 6 ut. So the final answer is this 6 plus our cosine multiplied by ut. Okay, thank you.